Okay, so welcome to chapter 5. This is one of my favorite chapters, and the reason I really like it is, first of all, it's not that hard, and second of all, it's extremely powerful, and it's not just for fluid mechanics, it's for everything. And we talk about it in fluid mechanics because fluid mechanics gets so complicated that you resort to experimentation, probably the most of any field out there. So that's why this chapter is in fluid mechanics, but it really can apply to anything, like I said. So the motivation for dimensional analysis and similarity is really all about cost and how we want things to work. So let's say we're designing a turbine for Voith, and you can see from the size of this is a human. This is like a 6-foot man standing there. That these things are huge, so you don't want to just do some back of the envelope calculation, hope your turbine design is going to work, go ahead and build this multi-million-dollar piece of equipment and install it in the field to see if it's going to work. So instead what you're going to do is you're going to start your design with computer simulations. Okay, and they'll give you a lot of information, but they're not always super accurate. So then what you want to do possibly is go to model testing or experiments, and that'll give you more information. So this chapter is really all about the experiments, okay? And you'll find that what you want to do when you're doing experiments is convert everything to non-dimensional parameters, and that will save you a lot, and we'll talk about that right now. It also allows you to do scale model testing. Because, for instance, you don't want to build that gigantic turbine, you want to build something smaller, test it, but what you get, your efficiency and all that kind of thing that you get from that turbine, the power, is not going to be the same on the model as it is the prototype, so we're going to learn how to scale that up. Okay, so let's pretend that you are designing a wing. You work for Boeing, you're designing a wing, okay? And you want to figure out what the lift is, for instance. So lift, as you imagine, is the upward force here. Drag is the force in the direction of the flow. Okay, so lift is one of the things we're really trying to find. And there are going to be some parameters that lift is going to depend on. One of those is chord length. Okay, that's just the length of this wing. Angle of attack, call that alpha. Velocity, and your fluid properties, rho and mu. Okay, those are all going to affect what kind of lift we get. So our first motivation is, again, it's a big wing, unless we have a gigantic wind tunnel, and even then we don't want to build these gigantic wings. What we want to do is test a scale model. Okay, so what we need to do is create a smaller size one, but it has to look exactly the same. All the angles have to be the same, and everything is just scaled down exactly the same. So this one is an 8-meter wing, so it's scaled down to 0.8 meters, so this is a 1/10 scale. But it has to look exactly the same, just 1/10 scale. And it also, we're going to have to run it at that same, see how it's 10 degrees, all angles have to be. So this is geometric similarity, when you have it all the same, just scaled down or up. Okay, that's the easy part. We also need to get what's called dynamic similarity and kinematic similarity in order to do scale modeling. So for dynamic and kinematic, so movement and time based, that means all non-dimensional parameters must match. So we're going to have to figure out how to come up with these non-dimensional parameters we're talking about. Must match. So all non-dimensional parameters must match. Okay. So that's one motivation, and that's to do scale modeling. Second motivation is just experimentation in general. Okay, so we've decided here, or I've decided for you, that the lift is going to be based on these things: chord length, angle of attack, velocity, and the fluid properties rho and mu. Okay, this means lift is a function of these things, and this function is going to depend on your wing shape. Shape of wing gives your F. Okay, and when I say a function of, that means, you know, L equals C squared minus alpha plus V. Of course, all the units have to work out. That kind of thing is a function. Okay. So in order to do an experiment, knowing that lift is a function of all these things, we want to figure out, okay, how do all these different parameters affect lift? We can do some experiments. Okay, and what you could do is just, you know, set all the variables but one, all the independent variables over here on the right hand side but one, vary them one at a time, and then measure lift. Okay, what'll happen then is if you say have 10 different alphas, okay, and 10 different chord lengths and 10 different rhos and mu's, you're going to end up with 100,000 experiments. 100,000 experiments is pretty expensive and takes way too long. Okay, so we can't really do that. What dimensional analysis does is change that from 5 independent variables down to just a couple. Okay, so if we use dimensional analysis, and we're going to do this as an example in a little bit, you're going to find that lift over rho v squared c squared equals a function of rho v c over mu and alpha. Okay, so now we have 2 independent variables. And we have 1 dependent variable. Well, we're always going to have 1 dependent variable. That's what we're trying to find. All these are dimensionless. Okay, and all this comes from just that concept of dimensional homogeneity. I can't say it. Homogeneity. And we can also give these names. So like we did in the lab with coefficient of drag, you can say this is the coefficient of lift, that left-hand side, and if you recognize there's a Reynolds number thrown in there, and we say sub C because the length scale is chord length, and then alpha also. So CL was our dependent variable, L over rho v squared c squared, and that's called a lift coefficient. And Reynolds number, rho v c over mu. Okay. So now if we want to do experiments and figure out our lift, what we can do is just vary alpha and Reynolds number. That's 2. Now we need 100 experiments. Before we needed 100,000 experiments. Now we need 100 experiments. We can do 100 experiments. That's not that hard and not that expensive usually. So all this again comes from that principle of dimensional homogeneity. Okay, so once we do these experiments, another good thing about dimensional analysis is since we only have 2 independent variables, 1 dependent variable, we can graph these things, kind of like you saw for the sphere and the drag coefficient, or we can put them in tables, or we can come up maybe with equations, maybe that F, we can come up with an equation for it. But our experiments give us that F of, so it tells us how they're related. F of Reynolds number and alpha, okay? And you can graph that in various ways. So if you only have 3 variables involved, you could do something like this. Coefficient of lift, usually your y-axis is your dependent variable. And you could put Reynolds number or alpha here, either one, and then do some other ones here. Usually it would look like that. Okay. This graph now that you have is going to work for any size and shape, or not shape, but any size at any velocity So you can use this for models as well as prototypes, which is really, really powerful, okay? But these variables have to be non-dimensional, okay? So what you gotta do if you're doing these things is equate the non-dimensional variables between your model and your prototype. The prototype's the big one. So if, for example, we had coefficient of lift from before, which is L over rho v squared c squared, equals a function of Reynolds number, which is rho v c over mu, and alpha, what we need to do if we want to, for example, we're given some information about a full-size wing. It's going to fly in air, and it has a chord length of 3 meters at a velocity of 175 meters per second and 8 degrees. We want to find the expected lift for the real wing given our experiments or graphs. So let's say we did a model test. We found this all using small models, and now we want to use that in order to figure out what kind of lift we're going to have on the real thing. Okay, so the first thing you got to do is equate your independent variables, over here. So you need your Reynolds number, rho v c over mu, and if I plug all that information up above, I get 6.3 times 10 to the 7th. Okay. So let's say we have that graph up above, this graph, and we're able to read that for this alpha that we have, and this Reynolds number, 6.3 times 10 to the 7th, we got a coefficient of lift 0.9, okay? So if that was the case, we would put in 0.9 is CL, and then we can rearrange and plug in, and you end up with 298,000 newtons on the prototype, based on stuff we did on the model. Okay, so that's how you do similarity or scale modeling, and we're going to cover that more later. And again, here's just like the method that you use for this similarity. You want to first find the range of Reynolds number that the real wing would fly at, and then when you did the test, the model size test, you would get the same range of Reynolds number. Okay, that means you're going to have to probably scale up the velocity if you're still using air, or change the fluid or something in order to be able to test at those same Reynolds numbers on the model. You measure the lift on the model, but with that lift then you go ahead and calculate the coefficient of lift for your model tests, and then you can make those graphs, and with those graphs then you can figure out what that coefficient of lift is at the real Reynolds number that you're going to use. Okay, and then you can calculate the actual lift. So go ahead and do the first couple quiz questions.